In this video, I want to define fields and talk about some basic properties of them. A field is a commutative ring with unity in which every non-zero element is invertible. And fields are of the utmost importance in mathematics. For example, Q, R, and C, my rationals, my reals, and my complex numbers, are all fields. There's also finite fields. For an example, Z5 is a finite field. In elementary mathematics, we learn a very important property that says if AB is equal to 0, then one of these things must be 0. A is equal to 0 or B is equal to 0. Or both. And while this is certainly true if the numbers are real or even complex, it's not true all the time. As an example, if I consider Z6, 2 times 3 is 6, which in Z6 is the same thing as 0, but 2 is not 0 and 3 is not 0. So it's not always true. With this idea, I want to define this divisor of 0. So we have a non-zero element A is known as a divisor of 0 if there is a non-zero element B such that A times B is equal to 0 or B times A is equal to 0. Going back to my example in Z6 where we said 2 times 3 is equal to 0, that tells me both 2 and 3 are divisors of 0 in this ring. In addition, 4 is also a divisor of 0, since 4 times 3 would also be equal to 0 in Z6. As another example, let's consider the set of all 2 by 2 matrices with real entries. This does form a ring, however, it does have divisors of 0. We could do 0, 1, 0, 1 times 1, 1, 0, 0. And if we work this out, we would get 0, 0, 0, 0. So I have 2 matrices that multiply to give me 0. Another big property in elementary algebra that we learn is that if AX is equal to AY, then we must have X is equal to Y. But once again, this does not necessarily have to be true. Once again, let's go back to Z6. 2 times 5, well, 2 times 5 is 10. Mod 6 would be 4. That's the same thing as 2 times 2, which is also 4. However, this does not imply that 5 is equal to 2. We cannot cancel the 2. We cannot divide by 2. So we don't have this cancellation property in rings. So we have a theorem that says a ring has the cancellation property if and only if it has no divisors of 0. So let's look at proving this. Let's suppose that A has the cancellation property. We then need to prove it has no divisors of 0. We start by assuming AB is equal to 0. We need to show that neither A nor B is equal to 0. Well, if A is equal to 0, then we're done. So let's assume A is not equal to 0. Then we have that AB is equal to 0, which is also A0. Using the cancellation property, I can cancel the A's and get that B is equal to 0. So if A is not 0, B must be. And that shows me that I have no divisors of 0. Next, let's go the other way. Let's suppose A has no divisors of 0. We need to show it has the cancellation property. Let's suppose AB is equal to AC, where A is not equal to 0. Then we know that AB minus AC, well, we can factor out an A, so AB minus C. In addition, since AB is equal to AC, then AB minus AC must be 0. So now I have that 0 is equal to A, B minus C. I know there are no 0 divisors, so I know that one of these must be equal to 0. Either A is 0 or B minus C is equal to 0. We've already said this case was impossible. We can add C to both sides to get B is equal to C. So therefore, we have the cancellation property. Finally, I can define an integral domain. An integral domain is a commutative ring. It must have a unity, so a commutative ring with unity. And we must have the cancellation property. Alternatively, we can define an integral domain as a commutative ring with unity and no divisors of 0. It's easy to see that every field is also an integral domain. Having the idea of a multiplicative inverse can guarantee our cancellation property. If we say AB is equal to AC, we can just multiply both sides by the multiplicative inverse. So if we have the idea of identities, we definitely have the cancellation property. However, the inverse is not true. An integral domain does not necessarily mean a field. As an example, Z are integers. We've already discussed how these are a commutative ring, since the integers are commutative under multiplication. It does have a multiplicative identity element, 1, and there's no divisors of 0. Also, the cancellation property absolutely does work in the integers. However, we do not have inverses. So this is an example of an integral domain that's not a field.